Welcome to the next session, session 9 of exercise 1.2 real numbers chapter. Okay. Now till now we studied the two different statements, Euclid's division lemma and the fundamental theorem of arithmetic, and using these statements how to find the LCM, HCF, prime factorization, these things we saw. Now the next property that you have to remember, I am not telling that you have to learn, it's already learnt, you have to remember. That is what? The product of any two numbers, it's only for two numbers, not for more than two. The product of any two numbers is equal to the product of their LCM and HCF. Okay, the product of their LCM and HCF. Okay, that is the product of the two numbers is equal to the product of their LCM into HCF. That we will write. Now here the fourth sum is using this property, you have to do that. Okay, you can even verify this, which was studied in your earlier classes. You just select any two numbers, say 2, say 5. Now what is the HCF of these two numbers? Obviously 1 is the HCF. If you take the LCM of no common factor, so product is the LCM. So HCF into LCM gives you what? What is the product of these two numbers? 2 into 5, 10. So this is how you should always try to relate the concept that you are going to study or studying. With small numbers you can try. And of course it is very simple. So you can easily understand by if you are able to apply this in small numbers. Okay. So in this sum also we are going to do like this. The product of any two numbers. So the moment the numbers are given, you immediately don't start doing the HCF. You are not supposed to do that. You have to get an equation, and from that equation you have to solve it. Okay. Now I will write the product LCM into HCF is equal to the product of the numbers. The product of the numbers. Okay, this is the concept. Now this concept you are going to apply. How are you going to apply? 306 into 657. Okay, I'll write like this. That is 9 into LCM. HCF is given to be 9. Therefore, 9 into LCM is equal to 306 into 657. So, this is the statement. Therefore, what is the LCM is equal to 306 into 657 divided by this 9 comes down. Okay, this is the result. Okay. Now this is HCF, therefore both the numbers are divisible by 9. So if you do so, you will get 2 9s, 3 9s are 27, 3 and 6, 34. So 657 multiplied by 34 is the LCM, multiplied by 4, 20, 22, 26, 3 7s are 21, then here 7, so 19, so you will write so you will get LCM is equal to 22,338 is the answer. That's how you should do it. Now here I would like to tell you this. This sum contains 4 different values. LCM, HCF, product, that is the two numbers involved. Out of these 4, any 3 is given, you can find the 4th. It may be LCM, it may be HCF, it may be one of the numbers. Okay, always it is possible by means of this equation. So, 5th question. Check whether 6 power n can end with the digit 0 for any natural number n. Here certain things you should think. Here n is given to be a natural number. Natural number starts with 1 to infinity. I have told you in the beginning itself. So n can take the value from 1 to infinity only. No negative numbers given. If negative numbers are given, in the place of n, if the value is negative, means you will get 1 by 6 power n. So obviously it's a fraction which is very, very less than 1 and so on, and the powers increase. Correct? So that also cannot be considered for this question. N is not 0. Why it is not given positive integer? When we say positive integer, 0 also will come. When we say whole number, 0 also will come. So when 0 comes, what happens? 6 power 0 for any value of 0 for any base, it is always 1. Again, the question is not to be considered. Therefore, it is given as n is a natural number. So this nuances you should note in a sum. Correct? Now, here, see, this type of sums have a peculiar format. So what you have to write as a first statement, any composite number, you have to write the statement, this is very important. Any composite number can be resolved or factorized, can be or written as a product of primes. Product of primes by the fundamental theorem of arithmetic. That is a very, very important statement that you have to mention here. Fundamental theorem of arithmetic. You have to write this statement for all the sums coming like this. So I will write here in inverted commas. Any composite number can be resolved or can be written or can be factorized or can be written as. So this word can be replaced by your convenient word. As a product of prime numbers, as a product of prime numbers you can put, or primes by the fundamental theorem of arithmetic. Okay, so if you write, so the 6 being a composite number, I can write 6 is equal to 2 power 3, where 2 is a prime number, 3 is a prime number. Therefore, 6 power n can be written as 2 into 3 the whole power n. You tell me what is this? 2 power n into 3 power n. Remember, n can take the values only natural numbers from 1 to 3, etc. 3 can take the natural numbers only from n to etc. Now here it's purely an analysis question. Okay, how? We have to find out for any power of 2, 2 power n can become 0 or not. If we want the ending digit to be 0, either this should have an ending digit 0 or this should have an ending digit 0. Now that we have to examine. Okay, so that I am writing here 2 power 1 gives you what? 2. 2 power 2 gives you what? 4. 2 power 3 gives you what? 8. 2 power 4 gives you what? 16. Now 2 power 5 gives you what? 32. 2 power 6 gives you 64. And then like that, what happens? 2, 4, 8, 6, 2, 4, 8, 6, the pattern repeats. So if you want, you can even verify 2 power 7 is equal to 128. 2 power 8 is equal to 256. So if you take the first 8 powers, the pattern, the ending digit is nothing but 2486. 2486. 2486, it just repeats. Therefore, for any power of 2, we cannot have the ending digit as 0. Clear? Are you understanding? Similarly, we have to analyze for 3 power. Now, I will write here 3 power 1 is equal to 3. 3 power 2 is equal to 9. 3 power 3 is equal to 27. 3 power 4 is equal to 81, 3 power 5 is equal to 243, and then 3 power 6 is equal to, one more 3, it is 729, and then like that if you keep so, write the products, just the pattern of the ending digit is 3971. And here we have got 3971, 3971, 3971. That way the pattern repeats again and again. Therefore, for any power of 3, we don't have the ending digit as 0. And similarly, for any power of 2, there is no ending digit as 0. Now, if you want, you can tell by mind also, nothing wrong. Next will be 3 power 7 into 3. What do you get? 2197. Isn't it? If you multiply 729 into 3, you will get 2187. Okay, sorry. Then 3 power 8. Again, the same 7 into 3. 1 repeats. So 3971, 3971, 39. That way it will repeat. Now, in order to practice this thoroughly, initially for some sums, you write all the powers up to 10. Similarly, for 3 also, you write all the powers up to 10. I will show you here. Okay, separately I will show you. If you want, you can take down. Okay, so 2 powers of n is equal to, for any power of n, it doesn't become 0. The ending digit doesn't become 0. Similarly, for 3 power n, for any power of n, the ending digit can become 0. Therefore, if you take the product, there is no chance that the ending digit is 0 for the product 2 into 3, the whole power n. Therefore, we can conclude 6 power n cannot become 0. Here you can write the reason. The reason I will show you. In order to understand better, once again I will write for you. 2 power 1 is equal to 2. 2 power 2 is equal to 4. 2 power 3 is equal to 8. 2 power 4 is equal to 16. 2 power 5 is equal to 32. 2 power 6 is equal to 64. 2 power 7 is equal to 128. 2 power 8 is equal to 256. 2 power 9 is equal to 512. 2 power 10 is equal to, it is 1024. Are you understanding? Look at the pattern 2486, 2486, 2486. It will keep on repeating. Similarly, you just write 3 power 1 is equal to 3, 3 power 2 is equal to 9, 3 power 3 is equal to 27, 3 power 4 is equal to 81, 2 power 5 is equal to 243, 3 power 6 is equal to 729, and 3 power 7 is equal to 2187. Isn't it? 3 power 8. So many times you won't be able to remember this value, so better you multiply. 2187 into 3 gives you 8 7s are 21, and then 8 3s are 24, plus 2 gives you 26. 3 2s are 3 1s are 3 plus 2 5. So 6561. Then 3 power 9. So 6561 you multiply by 3. Okay, so it is 19683, and then 3 power 10 is equal to, you multiply this also by 3, it is 9. 3 3s are 9, 3 8s are 24, 3 6 are 18, plus 2 20, 3 19s are 57, plus 2 gives you 59. So it is 59049. Now look at the pattern 3971, 3971, 39. So next 3 power 11 will be ending with 7. Isn't it? Next it will be, so 3971 pattern repeats. So in order to understand clearly, I have repeated once more. Isn't it? Once more I've done. If you want, you can take down these values for this particular sum. Got it? Up to 10 powers, if you are able to multiply and get it, you will be able to arrive at the pattern for the ending digit. So how will you sum up all these results and write the answer? For any power of 2, you can write here, for any power of 2 and 3, the ending digit is not equal to 0. Therefore, the product 2 in 3 cannot end in 0. Or we can write 6 power n cannot have an ending digit as 0. Cannot have 0 as the ending digit. You have to conclude like this. So only then it is right. Are you understanding? This is how you should conclude the sum. Now here, sixth sum. Explain 7 into 11 into 13 plus 13 and second sum. 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5 are composite numbers. Let us take the first one. I'll just mark a subdivision 1. 7 into 11 into 13 plus 13. Now here this is considered as a separate term. This is considered as a separate term. So this is multiplication with 13 and then there is a plus sign here and another 13. I'm going to take 13 out. So I will get 7 into 11. 13 is taken out. I am not disturbing that. So let us be like that. And here 1. So if you write it, what will happen? The entire number becomes a multiple of 13. The product, whatever you are going to get, is going to be a multiple of 13, isn't it? Or in other words, if you want to be convinced, it is 77 plus 1, that is 13 into 78. Therefore, the given number is a multiple of 13. Therefore, 7 into 11 into 13 plus 13 is a composite number with 13 as a factor. You have to conclude like that. With 13 as a factor. Are you understanding? This is it. Is it clear to you? That's it. Now go to the second subdivision. The second subdivision, we have 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5. This is a product of so many terms, so many numbers, and here it is plus 5, one single term. So if you look at this, it is 5 into 1 only, isn't it? So if you look at this, 5 is a common factor. So I am taking that 5 out. If you exclude that 5, the first term becomes 2 into 1 plus 1. That means what you are writing? You are writing this as a product into 5, as a product of 5 or a multiple of 5, or for the big number 5 is a factor, correct? Therefore the number is, you don't even have to multiply and write. Simply if you are able to write 5 times some number, that means for the whole number 5 is a factor. Therefore you are concluding that the second subdivision number, namely 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5 is a composite number. Is a composite number with what as a factor? With 5 as a factor. You have to conclude like this. This is enough for you. But in order that, you want to find out and then you are not satisfied with this explanation, means what you can do in the rough column, you just multiply. 7 into 6 gives you 42. So 4 into 3, 12. 12 into 2 gives you 24, correct? So 24, and then there is one plus. Now multiply this. 24 2s are 48. 4 carry over. 24 4s are 96 plus 4 gives you 100. So that gives you, you'll get 1009 multiplied by 5. Therefore, you are able to write this as a multiple of 5. It is only a rough work. It is for you to understand. I have written like this. Simply if you are able to write as a product with 5, or in other words as a multiple of 5, or we can say with factor as 5, that means you are concluding that it is a composite number with 5 as a factor. That's enough. for explanation. Okay, so I want you to practice more sums like this. There are few sums given as worked out example. You please go through and be thorough with this concept. In the next session, we are going to see the application sums for LCM and HCF. Few more examples. Okay, wish you all the best.